My name is Chu Han. I'm from Wisconsin. So I really like the previous challenge paper. They proposed a lot of compelling concerns on today's LPWAN. And in this paper, we are trying to make a small step and work on the capacity issue. So hopefully this talk will give the authors more confidence about the future of low-power WAN. So in the paper, we propose a blind distributed MIMO technique for narrowband IoT, where we completely remove the coordinated channel measurement phase and enable MIMO multiplexing for vast throughput increase. So I'm presenting on behalf of all the other authors of the paper, Mehdad from University of Washington and Krishna and Boldy from Microsoft Research. I also received tremendous support in the project from my advisor, Suman. So before describing the technique, I would like to first introduce a new frequency band for long-range IoT applications, which has not been widely used for IoT in the past. So a large number of urban rural IoT applications, such as smart cities, smart agriculture, require long-range wireless connectivity. Longer range helps cover a vast geographical area with fewer base stations and consequently lowers the network deployment and operational cost. Existing wide area networks use either the unlicensed ISM bands such as LoRa and Sigfox or rely on cellular connectivity. In this paper, we explore the use of 150 to 174 megahertz VHF spectrum comprising unlicensed multi-use radio service, which we call MURS, and licensed narrowband channels. The key advantage is a significantly superior range. The orders of magnitude higher coverage is fueled by two key factors: 200x higher power transmit allowance by the FCC, and the more superior radio propagation characteristics at a much lower carrier frequency. The frequency band contains both licensed and unlicensed spectrum. The table below shows the 5 channels in the unlicensed MURS band with either 11.25 or 20 kilohertz bandwidth, and FCC requires FSK modulation in this frequency. Apparently, one limitation of this new frequency band is the low bandwidth, which makes it only suitable for low data rate applications. To evaluate the coverage, we conducted a large-scale measurement study in Seattle area where we install a number of MURS radio transmitters on a fleet of 90 utility vehicles that drive around the area. With a single base station located on the rooftop of an office building located in Redmond, we are able to cover a huge area. On the map, you can see that with a single base station on the top right part of the map, we can basically coverage the entire Redmond, Bellevue, and even part of Seattle. And we collect over 300,000 uplink messages per day from all the vehicles. In the measurement, we obtained RSSI from both MURS and LoRa transmissions. Now, both LoRa and MURS devices were transmitting at the highest power possible allowed by the FCC, and they were transmitting at a similar data rate, to be fair. We can see that under the same condition, MURS band achieves 5 times the range compared to LoRa, which translates into a 25-time higher coverage. This vast increase in the coverage is great. However, the increased geographical coverage also translates into a larger number of IoT devices covered by the same base station, which calls for higher uplink network capacity. Given the limited amount of bandwidth available in both the licensed and unlicensed spectrum, which is only 24 megahertz in total, apparently we have a capacity issue. So distributed MIMO offers the promise of scaling the network capacity by enabling base stations to decode concurrent transmissions in a collaborative way, which we will use to increase the network capacity. If you still remember from the last talk where the speaker was calculating the the effective throughput of LoRa, there is a devastating 18% multiplied on the throughput, which is caused by Aloha excess. Here, we are trying to remove that 18%. In order to enable simultaneous decoding of multiple concurrent transmissions using distributed MIMO, the channel parameters and the carrier frequency offsets for all participating transmitter and receiver pairs must be known for channel encoding. Therefore, communications in existing MIMO system typically alternates between a measurement phase and a transmission phase. In the measurement phase, all participating transmitters and receivers coordinate to first conduct channel measurement. After the channel measurement, all the transmitters start to transmit concurrently. However, expecting this manner of coordination between IoT transmitters and the base stations, as well as the resulting measurement phase overhead, is not a viable option for IoT devices. This is because typical IoT devices predominantly sleep most of the time, which means they will turn their radio off to save energy. And they only wake up on the occurrence of events to transmit a short notification message, typically a few bytes, after which they go back to sleep. Consequently, coordination is very difficult to achieve in typical IoT networks. In this paper, we are presenting a new technique named IRIS, blind distributed multi-user MIMO, that eliminates the need for any coordination and the measurement phase at all. Using IRIS, IoT devices are able to simply transmit at any time, arbitrarily, and would require no modification to the transmitter either, which means we are improving the capacity without posting more energy consumption issues on the transmitter side. Let's first take a look at, from a high level, how IRIS operates. The IoT transmitters modulate the data into complex IQ samples and transmit them arbitrarily without any coordination. As a result, their transmissions are well likely to be concurrent, causing interference. The signals from concurrent transmissions linearly superimpose in the wireless channels and are received at multiple base stations. Without IRIS, suppose we are simply using Aloha access. For most modulations, the concurrent transmissions, the interference from the concurrent transmission will simply cause the demodulation and decoding to fail, diminishing the throughput. So here, to enable IRIS, we leverage a key property of MERS and VHF narrowband channels. Unlike wider channels, they can be represented by a single complex number. Through a measurement study, we find that the delay spread of the channel is much smaller than the required Nyquist sampling rate. In addition, for distributed MIMO, an important issue is the ability to synchronize base stations down to a sample level in order to enable MIMO decoding. Here, we are able to synchronize them using only GPS timestamps, thanks to the low sampling rate of the narrowband channels. The base stations, on the other hand, they do not attempt to decode at all. Instead, they are forwarding the raw IQ samples to a central entity in the cloud. This is also possible due to the low sampling rate. Using the received IQ samples and the known preamble sequence, IRIS forms and solves a set of nonlinear equations in real time in the cloud in order to solve the unknown channels, CFOs, and the data samples at the same time. This allows IRIS to decompose signals into multiple IQ sample streams corresponding to individual transmissions. Once the IQ sample streams of each transmission are separated, the decoder can now demodulate each stream separately in the standard way, not using MIMO. They're simply trying to demodulate a single IQ sample stream as in normal operation. The ability of IRIS to recover individual IQ sample streams from concurrent transmissions allows it to perform distributed MIMO even for nonlinear and phase non-coherent modulation schemes, such as FSK, which is necessary because it's mandated by the FCC in this frequency band. So IRIS completely removes the need for a dedicated channel measurement phase. It allows the device to transmit as usual, independently and at any arbitrary time. The key challenge IRIS overcome is to reliably estimate CFO and the channels between the transmitting devices and the receiving base stations using the preamble while simultaneously recovering the IQ samples of the other transmissions. Next, I will briefly cover the key operations of Iris. Iris has 3 distinct phases of decoding: idle state, steady state, and most importantly, what we call a blind estimation state. It starts in the idle state, which corresponds to when there are no ongoing transmissions at all. In the steady state, the CFOs and the channels have all been estimated for all current transmissions. Therefore, estimating the next IQ samples for each transmission is absolutely similar to standard MIMO decoding. More importantly, we will see how Iris can reach steady state using blind estimation. Upon detecting one or more new preambles indicating new packet arrivals, it transitions into the blind estimation state. In this phase, Iris decodes the concurrent transmissions IQ samples while simultaneously estimating the channels and CFO for the new transmission, after which it moves back to the steady state and continues to recover the IQ samples. Now let's see how blind estimation works. Consider a scenario where we have 2 concurrent transmitters and 3 receivers. TX1 starts earlier and is already in steady state, which means its channels and CFOs have been estimated. Now, a new transmitter, TX2, starts to transmit the packet's preamble sequence. For TX2, the preamble samples are known. However, the channels and CFOs must be estimated, which are marked in red. So essentially, Iris is trying to accumulate enough equations so that it could solve all the red unknown variables. In practice, Iris decomposes this problem into 2 parts. We use a standard MSE approach to solve all the linear equations, which do not include the CFO. Apparently, it's nonlinear. CFO is obtained through solving a nonlinear optimization problem that is trying to minimize the residue error in the MSE. After successfully solving for these channels and CFO parameters, Iris moves back to the steady state and continue to decompose the sample streams. The details of the algorithm can be found in our papers. To evaluate Iris, we deploy 4 USRP base stations around Microsoft campus in Redmond. And we were driving around the city carrying 3 transmitters that are sending packets concurrently. We collected measurements from 17 different locations. So we were comparing Iris against a range of different schemes. The key insight, though, is that Iris can achieve around 80% packet successful rate. Well, the rest of the schemes basically fail completely under packet collision from the concurrent transmissions. To summarize the work, we conducted large-scale measurement studies and showed the superior coverage of a new frequency band, 150 to 174 megahertz VHF spectrum, which can be used for long-range IoT applications. To scale the uplink network capacity to the larger number of IoT devices, we propose a blind distributed MIMO technique where we completely eliminate the dedicated channel measurement phase and allow the IoT devices to transmit arbitrarily. And for now, we are working to extend this technique to wider band protocols such as LoRa. So this concludes the talk, and I'll be happy to take any questions. Thank you.